Now, xt_2, this command is more powerful than xt_, because xt_2 it has some additional features. So, what I will do, I will first estimate the model, same type of model, system and difference GMM. First, I will start with difference GMM using the xt_, command. So, this is xt_2, and then what I need to specify is my dependent variable, which is n, and then I am taking its lag also NL1, and then let me take NL2 also. Look at now the difference between xt_, and xt_2 command. In xt_, I was specifying only n after xt_, command, but here I am putting NL1 and NL2 as well, because I would like to use 2 periods lag, right. So, that is the difference between the command of xt_2 and xt_, and then I will be taking W, then WL1, then I will take capital, and then KL1 and KL2, first and second order lag of capital, and then I am taking WS also, okay, and then YSL1, YSL2. So, first and second order lag of industrial output, and then what else I will take, and then I will put YR, that means year specific dummy, YR star. Now, in this xt_2, after specifying your basic model, that means what I have specified, my dependent and all my independent variables, I need to specify which are my GMM type instruments coming Arellano-Bonds logic, and which are the instruments coming from the standard logic. Each of the predetermined variables, which includes lag dependent and other exogenous variables, they are actually, they themselves are their instrument following that standard logic, right. So, my GMM type instrument, I need to specify GMM and then NL1. So, this is my only instruments coming from Arellano-Bonds logic GMM type, and then after that I will be specifying IV style, that means IV within the bracket W, all the variables W, then WL1, then I have capital, then capital 1, KL1 and KL2, and then I have YS, then I have YS of lag 1, YS of lag 2, and then I have ER dummies. So, these are all my standard instrument. So, that means basically I am specifying which is my endogenous variable and what are the variables which are predetermined, which may include lag dependent and exogenous variables. And then to specify that I am considering only my difference equation, I need to specify that I do not need no level equation. By specifying no level equation, I am basically specifying a difference GMM. I am asking Stata that I do not need the level equation to be considered. If you consider, then it will become a system GMM. Since I do not need that, I am specifying no level equation. I also need robust estimates. I also correct for small sample bias. If you recall, we initially said the dynamic panel data model is best suited when T is small, N is large. So, that is why I need to correct for small sample bias, and then lastly I also need to put no cons command. Okay, why no cons? Because this equation is in differenced form. So, when the equation is in difference form, obviously you do not get a constant for that. I need to put no cons command, right. If you put that, it is not able to recognize xt upon 2. So, I need to install sorry, this command is also not taking ssc install xt upon 2. Yes, now it is installed. So, I will put the command now. So, xt upon 2. So, please keep in mind, if you have a licensed version of this data and at any point of time if you get this unrecognized command, then automatically you should install that using xt upon ssc install and that particular command. Now, look at, I got the same estimates, but yeah. So, this is basically the difference GMM, but you see in the difference GMM the coefficient is 0.68, that means it is still lower than the lower limit specified by 0.73. Lower limit was specified by the fixed effect model. So, that means all my difference GMM you see the coefficient is not lying exactly within the interval as I have specified. Anyway, for the time being, let us see what I have installed here. So, I have estimated this model, this is what I have estimated, the dynamic panel data estimation one step difference GMM, right, one step difference GMM, and these are the coefficients, and once again how many number of instrument is 41, and these are the instruments. For first difference is difference of all these, that is a standard, and what are the GMM type? From lag 1 to lag 8 NL1. Since I have specified my NL1 is the only endogenous variable, then by putting that xt upon 2 command, Stata has actually considered from lag 1 to lag 8 as the instruments or for this NL1. These are the instruments, right. And again you see Arellano bond test AR1 which is there, that means the z value probability get the p value is 0.0000 and this is 0.606. What does it indicate? Basically it indicates that presence of AR1. What about the over identifying test that we are talking about? We will look at the Hansen test of over identifying restriction, which is 0.177. So, both the tests, Sargent test as well as Hansen test, they are test of over identifying restrictions. Please keep in mind, you can go back to my earlier lectures on instrumental variable estimates. we need to be very careful about the null hypothesis of the Sargent and Hansen test. In both the tests, actually, the null hypothesis is that over-identifying restrictions are valid, right? When over-identifying restrictions are valid, that means my null hypothesis should not be rejected. While both the tests ideally should produce results in such a way that my null hypothesis should not be rejected, Sargent test indicate my null hypothesis is rejected, but since this is not a robust test, we will generally go for Hansen test of over identifying restriction, which is a robust test, and that value p value is 0.77. That means my null hypothesis of over identifying restrictions are valid, that is not actually rejected. So, this is how we have estimated the difference GMM using the XT-ABORN2 command. What are the advantages of this command? This command produces both the post estimation checkup results simultaneously. I do not need to put again stat ABORN then AR test 4 separately. So, it is giving test of autocorrelation, test of over identifying restrictions together. Right. Now, once we estimate this model, see, so far when we are estimating the model, how we are transforming the variables? We are transforming the variables in this way, yit minus yit minus 1. This is called first difference transformation. First difference transformation. Now, this first difference transformation, it has a serious drawback. What is that? If any observation is missing, if any of the YIT is missing, then what happens actually, it magnifies the gap in unbalanced panel. Unbalanced panel means some of your observation might be missing. Okay. We cannot assume, for example, in this particular context, when you are discussing 140 firms data about the employment and all other variables, it may so happen that a particular firm's observation is missing in a particular year. Okay. If it is missing, then what will happen? Neither delta YIT minus 1 nor delta YIT plus 1 will be available. If the observation itself is not there, how will you take its previous value and how will you take its next value? If my observation for second period for a particular firm is missing, then when I am taking this first difference transformation, then what will happen? For the third period also, I cannot get that, right? So, first difference transformation, if we apply in unbalanced panel, then it basically magnifies the gap, because delta YIT plus 1 will be missing, because delta YIT itself is missing. So, to combat with this problem, there is a suggestion given by Arellano and Bover 1995, which is called forward orthogonal transformation. This is very important. Please keep in mind, forward orthogonal transformation, that what we are discussing here is very important when you have unbalanced panel and trying to estimate it by first difference transformation, right? So, what we are doing here, this is called forward orthogonal transformation or in short FOD. Okay. Sorry, this is not forward orthogonal transformation, this is forward orthogonal deviation. Deviation, DEVI FOD, forward orthogonal deviation. This is suggested by Arellano and Bover 1995. So, what they say basically that first difference transformation, FD transformation, has a major drawback. What is the drawback? If any observation is missing, as is the case in an unbalanced panel, as is the case of an unbalanced panel, then both yi delta yit and delta yi t plus 1 are missing for absence of yit. So, basically what it says, if yit is missing, then delta yit and delta yit plus 1 both are missing. Okay. Then what will happen? That means basically, that means this basically magnifies the gaps in unbalanced panel. Okay. What is the solution? Solution is so in an unbalanced panel for FD transformation. So, what is the solution? Solution is now that FOD, what we are talking about, what they say that instead of subtracting yi t minus 1, that means which is basically the previous observations from the contemporaneous one, contemporaneous is yit, from the contemporaneous one what will subtract? we will subtract the average of all future observations. Okay, all future available observations. We will subtract average of all future available observations. Okay, all available future observations. So, no matter how many gaps, so that means no matter how many missing observations are actually there, it is computable. Since I am taking average of all available observations, it is computable for all observations except for the last one. Because in the last period there is no future observations available, so I cannot take FOD for the last period's observation. Otherwise, last to last observation, whatever information is available, I can take average of all the future available observations and then I can subtract that from YIT. That is the difference. So, instead of subtracting YIT minus 1 from YIT, which is basically magnifying the gaps when YIT is missing, some YIT is missing, what I am subtracting from YIT? The average of all future observations. So, that way, even if some of your observations are missing, then it is computable for all the observations except the last one. So, in short, precisely what I am doing, so what I am doing here, so my transformation will look like, then will look like WIT. So, what will do? WIT. So that way what will happen? Except the last one, so it minimizes the data loss. Okay, it minimizes the data loss. And what is basically this FOD transformation? To be very precise, then just one second. So, to be precise, my if W is a variable, then the FOD transformation is, I am denoting WI t plus 1 with this sign. This is called FOD transformation, which is nothing but what I am doing, CIT into WIT minus 1 by capital TIT into sum of WI small s, where small s is basically greater than t. So, all available future observations, okay, where CIT is basically equals to TIT divided by TIT plus 1. Okay, and what is TIT, capital TIT? TIT equals to number of all future observations, number of all future observations. So, if you have unbalanced panel, then we should use the FOD transformation in place of first difference transformation. But if the panel is balanced, then both FOD and FD produce similar results. Okay, no need of going for FOD. So, now the question is, how do you estimate this model with FOD transformation? We will once again do that, right. So, we will go to our model once again, and then again that xt upon 2, xt upon 2, and then my dependent variable, and again NL1, NL2, and then my W, which is wedge, W, and then WL1, WL2, sorry, WL1, and then I have capital, then capital of lag of order 1, order 2, then I have YS, then YS1, YS2, okay. Then I have here. So, this is how I have specified my model. Then I have to put what is my GMM, right. That means what is my endogenous variable, which is in L1, and then what is my IV? IV is all other variables, that means W, starting from W, and WL1, and then capital, and then capital of lag 1, KL1, then KL2, then YS, and then YSL1, YSL2, right? And then what else is there in my equation? I have YR star. So, I will put YR star, and then what we have to do is we have to put two-step robust standard order orthogonal and no level equation. So, this orthogonal, in that command box, what is two step, that I will discuss later on. For the time being, please keep in mind our focus is on this orthogonal command, because this orthogonal command, if you put, then what is happening here, we are taking forward orthogonal deviation. Orthogonal means FOD transformations are used in place of first difference transformation, right. Now, look at instruments for orthogonal deviation equation, that is what we got, right. Once again, the NL1 0.72. So, that means this orthogonal deviations, since some of the observations are missing here, this is an unbalanced panel. Basically, what is happening, the moment we take orthogonal deviation in place of first difference transformation, my coefficient of NL1 has increased and it is just closer to 0.73, it is 0.72. Earlier, if you look at, my coefficient was 6.8. Okay, 6.8. So, from 6.8 to I got 0.72. This is the improvement what I got just by using FOD transformation. This is very important when you are working with unbalanced panel, and in reality it is quite likely that many a times you may have to work with unbalanced panel. You should not expect that all the firms, when you are working with a micro panel with several households, several individuals, several firms, that each of these firms will available for each of the period. There might be some missing observation, and in missing observation it is dangerous to use first difference transformation because it enlarges the gap. Okay, if it enlarges the gap, if YIT is missing, both delta YIT and delta YIT plus 1, both of them will be missing. As a result of which, what we should do is the FOD transformation that not only minimizes the data loss, okay, because I can now subtract, what I am doing, I am subtracting only average of all future observations. So, even if some of your observations are missing, I can always calculate average for all the periods except the last one, and that improves the coefficient efficiency a lot. Okay, as you can see, my coefficient is moving just towards the theoretically specified lower and upper limit. And then once again I got Arellano bonds AR1, which is again rejected, indicating the presence of first order autocorrelation, but second order autocorrelation is not there. And then as far as over identifying test is concerned, then Hansen test of over identifying restrictions is 0.17. So, that means over identifying restrictions are also valid. I will talk about all other outputs what we are getting over here in our next class. So, with this basically we would like to close our discussion over here. So, what we have mainly discussed in today's class, just the importance of that XT-ABORN2 command, how XT-ABORN2 command can automatically estimate the model with the two post estimation checkups presence of higher order autocorrelation and over identifying restrictions, all of them are readily available. We do not have to put any specific command for those. Secondly, we have also talked about another important concept, which is first, in place of FD, we have taken forward orthogonal deviation in case some of the observations are missing, and it is applicable in presence of dynamic unbalanced panel. So, with this we are closing our discussion. Thank you.